Hello calculus students, here we are with 4.2, basic differentiation rules and rates of change. What we're going to do here is, instead of going through that lengthy definition of the derivative every time, we are going to learn some derivative rules so we can quickly come up with a derivative for a variety of functions and apply them in things called rates of change with speed and velocity. Our first derivative rule is the constant rule. The derivative of a constant function is 0. That's because basically a constant is a horizontal line which always has a slope of 0. Here's a little proof. Notice a little tricky thing in the proof here. The limit as delta x goes to 0 of c minus c over delta x. It looks like you have 0 over 0 here. But actually c minus c is 0 and delta x is approaching 0. So whenever you have 0 over a non-zero number, that number is 0. Okay. And here's some applications of the constant rule. If you've got functions in various formats like this, y equals 7, f of x equals 0, s of t equals negative 3, y equals k pi squared, where k is a constant, all these are constant functions. Their derivative is 0. Now, we're going to go ahead and look at the power rule. And let's explore one of these from over here in this exploration before we get to the power rule so you can see where it's coming from. And we're going to use the definition of the derivative on, let's do this one, f of x equals x cubed. With f of x equals x cubed, we can look at the definition of the derivative as this limit as h goes to 0 of f of x plus h minus f of x all over h. All right, we talked about this last chapter. Now let's see how it applies to this rule, f of x equals x cubed. If f of x, so let's apply the derivative. We get the limit, the derivative then, would be the limit as h goes to 0 of f of x plus h, which would be x plus h cubed minus x cubed all over h. So we get the limit as h goes to 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. And then it turns out that we can cancel the x cubes, and that's key. When we do our general proof of x to the n, we're going to see that that's always going to fall out. And what's left then is the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed all over h. We divide through by h into each of those terms, and we get 3x squared plus 3xh plus h squared. Now we can plug and chug, and as h goes to 0, then this whole thing just ends up being 3x squared, because these two terms fall out. So there's your derivative, 3x squared. And I think you can see where the rule is going to come from now, because we started with the function x cubed. The 3 comes down in front as a multiplier, and we lower the power by 1. And that, friends, is our next derivative rule, the power rule. When you take the derivative of x to the n, you end up bringing the power down in front and raising x to 1 less power, x to the n minus 1. Okay. Here's their proof where they take the binomial theorem expansion general in the text here. And notice how this x to the n term is always going to follow with a minus x to the n. And you get all this other stuff left over. But all this other stuff has at least one delta x in it. So it's going to divide into there. But only this second term right here, n x to the n minus 1 delta x, has just one delta x in it. So now all the other ones still have a delta x. So as delta x goes to 0, these all disappear. And we just focus on this. So let's try using this power rule and come up with some derivatives. F of x equals x cubed, n equals 3. So the derivative is n, which is 3, times x to the 3 minus 1, or 3x squared. So that's a. In b, we have to rewrite g of x. Well, they already told us it's a 1/3 power. So the derivative of g is 1/3 x to the 1/3 minus 1, or 1/3 x to the negative 2/3. Or if we want to write it in the original format, 1 over 3x to the 2/3, or 1 over 3 times the cube root of 2. I would have been okay with this as well for your final answer. And let's try C. Y equals x to the 1 over x squared. Let's use our derivative notation like this. But first, let's change the formula. This is x to the negative 2 power, so n equals negative 2. So it's negative 2 times x to the negative 2 minus 1. And we get negative 2x to the minus 3. That's fine. Or if I write it in the original, since the original one didn't have any negative powers, you could write like that too, except either of those. Okay, and here's a little about what we talked about. We rewrote 1 over x squared as x to the negative 2. Many times you have to rewrite it before you can differentiate it to get it as x raised to a power. Okay? So keep that in mind when we're doing derivatives. Okay? Now, finding the slope of the graph. Find the slope of the graph of fx equals x to the fourth. Well, the derivative is so handy now. It's just 4x cubed. So in each of these parts now, in A, when x equals negative 1, the derivative at negative 1 is equal to 4 times negative 1 cubed. So it's negative 4. So that is the slope of the graph. In part B, x equals 0. F prime of x equals, f prime of 0 equals 4 times 0 cubed. And we get 0. C at x equals 1. F prime of 1 equals 4 times 1 cubed, and that's equal to 4. So there are the slopes. And let's check this on your graphing utility. Get out your graphing calculator, and here's how you can actually enter it in to find the slope at a certain point on a function. On the TI-89, to do this, you can go to derivative. The derivative key is right, it's a little d above the 8. So you have the blue key first and then hit D. So in the T89 you go derivative and then put in the function x raised to the 4. And you have to tell it with respect to what variable. So you can say x. And when you do this, it outputs a nice 4x cubed. Now that's if you want to find the whole derivative function. If you want to just find the derivative at a point or the slope of a graph at a certain thing, we say the derivative of x raised to the 4th with respect to x, and then put the width symbol down. The width is right there to the left of the 7, with x equals negative 1. And when you do that, it returns the actual slope at that point, negative 4. So a very useful tool, your TI-89. Now, let's come along here, find the equation of a tangent line to the graph of f of x equals x squared when x equals negative 2. First, we can get the derivative. It's just 2x. This will tell us the slope of all the tangent lines. We want the derivative at x equals negative 2, so we put negative 2 into the derivative formula. We get negative 4. And so now that's the slope of the tangent line equals negative 4. We need a point on the tangent line. Well, that's when you look at f of negative 2, which is negative 2 squared, which is 4. So you have the point negative 2 comma 4, and the slope of the tangent line that goes through that is positive 4. Let's look at some of these ideas. Here's the point negative 2, 4, and here's the slope of the tangent line is negative 4, so to actually get the equation of the tangent line, we can use point slope. Y minus 4 equals the slope, negative 4, times x minus a minus 2. So I put the point into point slope, and the derivative told me the slope of the tangent line. So now we can keep moving that around. Y equals negative 4x plus 2, so that's minus 8, but then we add the 4 from the other side, and you get y equals negative 4x minus 4, which is this tangent line right here. Now, the constant multiplier rule. This is essential that you understand that this is not the same as the constant rule. If it's just a constant, its derivative is 0. But if you're multiplying a function by a constant, the constant kind of comes along for the ride. It does not become 0. And you can see that in the actual proof here, where this constant multiplier can get factored out of these additions and subtractions and travel outside, because the limit of a product is the product of limits. That is true for limits. So this constant multiplier can move outside here. And as a result, we can do derivatives of many things here. Notice here in y equals 2 over x, you write as 2x to the negative 1, and now this is a constant multiplier. So here, first of all, we think of f of t as 4/5 of t squared. And now, when we do the derivative, f prime of t, the 4/5 comes along for the ride, the 2 comes down in front, and we take t to 1 less power the first. So that's how we get 8/5 t for the derivative of that. Here for y prime, 2 will just come along for the ride. And we bring the half down in front, x to the negative 1/2 power. So it just becomes x to the negative 1/2, or 1 over x to the half, or 1 over the square root of x. I take that or that. Now here, this is where it starts getting tricky. You have to really start thinking about how to rewrite these functions first as 1/2 x to the negative 2/3 power. Now we can do the derivative and say 1/2, this constant multiplier comes along for the ride, times negative 2, the power comes down in front, times x raised to the negative 2/3 minus 1. So we end up with a derivative of negative 1/3 x to the negative 5/3. And you can leave it as a negative power like that. Finally, with this, just got to realize that 3/2 is the coefficient. And x is being raised to the first. So we get for y prime just 3/2, the slope of this line. Because the 1 power comes down in front as a 1, and you raise now x to the 1 minus 1, or x to the 0, and x to the 0 is 1. Okay. Now, what I just did a lot over here was combining all to one rule, and that is just if you've got a constant multiplier in front of an exponential, x raised to the n, then you can use the power rule and the constant multiplier rule together. And I already did that in some of those past problems. We could see it again here too. But notice here in example 6, we focus on first rewriting the function here as 5 over 8x cubed. So it's 5/8 x to the negative 3. Rewrite it as a constant times x raised to a power. Now you can do the derivative. So we leave the constant multiplier in front, 5/8, negative 3 x to the negative 4, dropping it by a power. So it's very similar to this last one. But notice how in this case the 2 is raised to a power. I had to deal with that first. So I'm getting, simplifying the derivative, I get negative 15 over 8x to the 4th. Here, let's rewrite this as c 7/3 x to the positive 2. So that makes the derivative a lot easier then. It's 7/3 2 times x to the 1. So we get for the derivative 14/3 x. Down here, be careful. We might want to first, let's just move this whole quantity, 3x, is all being raised to the negative 2. Notice over here, and this is what's being talked about over here, the 3 was not being raised to the negative 2 power. Here it is. So I can rewrite it as 3x to the positive 2. So we get 7 times 9x squared, or 63x squared. So the derivative is 63 times 2x to the first, or 126x. Now, sum and difference rules. The derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference in the derivatives. Notice this does not apply to multiplication and division. We're going to have a whole other section on that next. And here's the proof where you can see how things get shuffled around. The f of x plus delta x is combined with the minus f of x to come up with the derivative of f of x. And here we're going to start using these sum and difference rules. Here someone took the derivative of x cubed and got 3x squared. The derivative of minus 4x and got minus 4. The derivative of the constant 5 was 0. So let's try it here together now. G prime then. We can take the derivative of this part, so we have a negative half coefficient that just comes along for the ride. Derivative of x to the 4th is 4x to the 3. Here 3x cubed, we bring the constant multiplier along for the ride, and x cubed becomes 3x to the 2, minus the derivative of 2x is just 2. So we get negative 2x cubed plus 9x squared minus 2. Now, some of the applications here. Rates of change. Something you remember from way back. Distance equals rate times time. So rate equals distance over time. And that was just fine if you're moving at a constant speed, or if you wanted to find the average velocity like you do in physics. Change in s over change in t, change in distance over change in time. And so you can find average velocity of a falling object just by finding 2 points. There's your position function, negative 16t squared plus 100. And you want to find the average velocity over these points here as change in distance over change in time. Well, I just this is all pretty much plug and chug. You put in S1, S2, get negative 48 feet per second, negative 40 feet per second from 1 to 1.5, negative 33.6 feet per second. Note that the average velocities are negative because the object's moving downward. This is an example of a ball being dropped from a 100-foot height. And here you can see that when you drop a ball, it doesn't move down at a constant speed. It accelerates. Now, if you want the instantaneous velocity, the velocity at a certain point on the function, then we have to go ahead and use the derivative, and then we call it the velocity. So it's not speed anymore. Here's the speed formula, but we take the limit as delta t goes to 0. So it's not just a change in s over change in time anymore. It's the limit as that change in time goes to 0. And we saw that you turn secant lines into tangent lines. You turn in an average rate of change. The secant line is basically an average rate of change. The tangent line is an instantaneous rate of change. And you may remember this formula from physics. Some of you can jot down your formula sheet. This is a position for a free-falling object. Its height at any time. It's 1 half gt squared plus v naught t plus s naught. And the various terms are defined in here. V naught is the initial velocity, g is acceleration due to gravity, and Earth we usually use negative 32 feet per second squared or negative 9.8 meters per second squared. And so we can look at this position function now. Use the derivative to find velocity of this thing. Time equals t, a diver jumps from a platform 32 feet above. And so this is the position function because 32 is the initial height. The diver is jumping up at 16 feet per second. So that shows that little going up there at that point. And here's gravitational acceleration. It's actually negative 32, but we take 1/2 of it for the position function. When does the diver hit the water? So to answer this first question, we have to set s sub t equal to 0. When is the position equal to 0? So 0 equals negative 16t squared plus 16t plus 32. Let's divide by negative 16. So we get 0 equals t squared minus t minus 2. And that factors t minus 2 times t plus 1. And so we get the diver hits the water at t equals 2 or t equals negative 1, which doesn't seem to make sense. I can see how it's 2 seconds later, yes. And the negative 1 seconds comes algebraically out of this because it assumes that maybe the diver did a whole parabola. And at 1 second before, so it's actually assuming the diver took off at a greater speed down here and hit a speed of 16 when they got up to the board and came around. Now, what's the diver's velocity to impact? So for that, now we need for this v prime, or the velocity, which is equal to s prime of t. So we take the derivative. The velocity is equal to, let's do this on the next page here. The velocity will equal negative 16 times 2 times t plus, I'm taking the derivative of this s function now, plus 16 plus 0. So our velocity equation is negative 32, oh that isn't squared anymore, negative 32t plus 16. And the velocity at impact then happens at 2 seconds. At t equals 2 seconds, we have the velocity at 2 equals negative 32 times t plus 16. So it's negative 64 plus 16, or negative 48, and our units on this one were feet per second. Notice it's not feet per second squared anymore, it's feet per second. And notice how the diver is moving faster here than way up here. Start off at 16, reached the velocity of 0 at the peak, and then started having negative velocities to indicate the direction is downward. And now let's look at some exercises. Number 50 is an interesting one here because you have to be careful. You can't just plunge in and take a derivative on this because you'll just get 2x plus 2 times 1, and that's just not right. And we're going to see that in our diagram in a second here. I'm going to expand it out. Y equals, using FOIL, x cubed. First outer is x squared, inner is 2x squared, last is 2x. So we have the original function is y equals x cubed plus 3x squared plus 2x. So the derivative is 3x squared plus 6x plus 2. And so at the point 1, 2, y prime of 1 is going to be 3 times 1 squared plus 6 times 1 plus 2. And so you get 3 and 6 and 2 is 11. And now it says find the equation of the tangent line, and we're going to check this against one of our pictures then. So the equation then of the tangent line, like the thing we did before here, use the point 1, 6 and the slope of 11. So y minus 6 equals 11 times x minus 1. Or y equals 11x minus 11 plus 6. And I'm just doing this so I can compare it with our calculator's answer. 11x minus 5. There you go. Let's set this up on GeoGebra. Okay, here we are in GeoGebra, and you can do this in your calculator too by entering in this function. And coming up with the tangent line. On GeoGebra, we can just click on tangent lines here, tangents, and you select a point, and then the function you want to do the tangent to, and there's your tangent line, 11x minus 5. So it all checks out. Now, some of you were thinking, did we have to do the derivative that way? What if we did the derivative as 2x plus 2 times 1, 2x plus 2? That would be the derivative function, and notice how that's different than the derivative function that we get of f of x here. Big difference. This is the one that we calculated by slowly expanding it out and then taking the derivative, and we got 3x squared plus 6x plus 2. This one is gotten by error. You can't distribute the derivative over a product and just take the derivative of each of these things in the product. Oh no, we're going to have something called the product rule to do that later. So there you go. There's our tangent line, and that's the derivative of the function that we calculated out earlier. Okay, in 55 here, we're trying to find k such that the line is tangent to the graph of the function. Now this seems very tricky because you can't just take a derivative of this because you don't know k yet. And here's the line, and we're supposed to get these two to be tangent to each other. Let's look at it visually. On GeoGebra here, I have a slider so I can change and look at different values of k. And here's the parabola, y equals x squared minus kx, and this point k is 2.1. And here's the line y equals 5x minus 4. I can slide this back and forth to come up with all sorts of possible solutions. Well, when is it tangent? It looks like something in here. But one way to tell when it's tangent is when you have exactly one point of intersection between, at least in this general area, between the line and the parabola. So we can go to intersection points. Let's intersect these two. And we get points A and B. And we want those to be just one point. So maybe we can slide around the slider here now to make that happen. Oopsie. There we go, we're grabbing it, sliding it. And here we go, A becomes B right around there. See, and then they disappear for a while when they don't intersect at all. It looks like right at -1. Right at -1. Now let's see if we can do this with our tricks from calculus. Okay, let's look at the line first. The line has derivative equal to 5. And we always knew that. The slope of the line is always 5. This parabola, it's going to have a derivative with a constant in it because we're going to get 2x minus k, because this is a constant multiplier and this is x to the first. So we just want to know, when do we get a slope equal to 5? So we can just set these two slopes equal. 2x minus k equals 5. And you can see the problem there? Because we're not getting one variable. We only have one equation with two variables in it, k and x. So we have to look at a different approach now, or get another equation somehow. That is, the slopes have to be equal. So this is setting the slopes equal. But to have a point of tangency, we also have to have the y-coordinates equal. The y-coordinates equal. So the y-coordinate here is x squared minus kx, and that's got to equal the y-coordinate over here, 5x minus 4. Now with those two equations, I think we've got something going here, because 2x minus k equals 5, and x squared minus kx equals 5x minus 4. Maybe even get rid of the k up here, or get rid of the x for that matter, and get solutions for k. So let's take a look. Let's solve this. So that's going to create variables. So let's go ahead and just solve this top one for k. All right. So let's split the screen again. K, 2x equals k plus 5. So k equals 2x minus 5. And we can put this expression in for k in the other equation. So x squared minus k, which is 2x minus 5, times x equals 5x minus 4. And at least we can get x solved for here. X squared minus 2x squared minus 5 is plus 5x equals 5x minus 4. The 5x's cancel. And so we get x squared minus 2x squared is minus x squared equals negative 4. So x squared equals 4. So x equals plus or minus 2. And then we can see what that gives us for k then. K is equal to 2 times 2 minus 5. And we get negative 1. So that's that answer for k we saw before. We also get 2 times negative 2 minus 5. And k equals negative 9. Oh, algebraically, I think we see an answer that we did not see in our big picture over here. Let's take a look again at these graphs. What is this k equals negative 9? Investigating this, we might not have seen it because I kept having k range between negative 5 and 5. That's the standard setting for a slider. So what we have to do is click on our slider. Stop the machine. We click on our slider and we change these from, let's say, negative 10 to positive 10, so we can have more ranges here. Maybe we'll just have the increment be 1 because we already see that our answer is going to be a whole number. Close that up, and now we got more options for our slider. Okay. Still not seeing it. You see it? K equals negative 9. Oh, sure enough, see, we had this point of tangency like this. K equals negative 9 starts hitting again. Let's see if we can't move the graphics for you to see that. And sure enough, when k equals negative 9, boom, there it is. Another point of tangency there. All right, flange out.